Hi, welcome back. Today we're going to continue our discussion of chain rule with multiple variables. Except for today we're going to take a look at what happens if we have two independent variables. Now, we saw the other day when we had w as a function of x and y. And the other day we said, well, we'll let x be a function of t, and we said y was some function of t. Well, today we're going to look at, well, what happens if our x is a function of s and t. So where x is now a function of two variables and y is also a function of two variables. Now, important to remember that these are our inside functions, which is where we get our chain rule from. These are inside functions. Remember, we're going to replace these into our function. So we could say w, which is a function of x and y, we could say w is a function of g s of t and h s and t, like so. So it's our chain rule function we are plugging in. Now, to get the partials then, to get our derivatives then, our total derivatives, we have to determine, well, first of all, which function are we going to take the derivative with respect to? Well, we now have two choices. The other day we only had t. Today we have s and t. So let's say we want to take the derivative of w with respect to t, with respect to s. Sorry about that, I can't spell very well. We would take our partial of x with respect to x times the partial of x with respect to s. This is just what we saw the other day. Here's the derivative of our outside. We're taking the derivative with respect to x, of w with respect to x, and then x is a function of s in this case, and now we take the derivative of x with respect to s, and that's our inside function. And we do the same thing with the y's. There's our outside function, and there is our inside function. And we can do the same thing with respect to t as well, where we would take the derivative of the function with respect to x, and then the inside function was x with respect to t, the outside function w with respect to y, and then the inside function, which is y, with respect to t itself. Now, again, these are examples of our total derivative, and we can keep the pattern going on for a very long time. We can do this with three or more variables. Now, another thing to kind of remember is we talked earlier this year where if this is a trace, this is a two-dimensional trace right here with one variable. This is x and y with respect to t. That's going to kind of like draw a line. But when we get to two variables, s and t, this becomes a 3D surface. So now we're talking about finding the derivative or the motion of a 3D surface right here. So let's take a look at some examples. We want to compute the partial of z with respect to t for each of the following. And we want to choose the appropriate chain rule. Now, when we're talking about the appropriate chain rule, we want to decide, well, would it be easier to substitute in, or would it be easier to just use our definition? I personally just like the definition right up here, the total derivative. So if I'm looking for the derivative with respect to t, well, we would get the partial z with respect to t, and that's going to equal the partial of x, there's my x, with this partial z, with respect to x, and then we multiply that by the partial of x with respect to t. There is my outside function. My outside function is x, and my inside function is with respect to t, because I'm plugging the t squared in for x. And I do the same thing with the y. It's the partial of z with respect to y times the partial of y with respect to t. There's our outside function, and there's our inside function. And you can do this mostly in your head. Ready? We can do this in your head. If I take the partial of z with respect to x, I can take a look here. Yep. That's a product rule. We would take the first times the derivative of the second, e to the xy times y, plus the second, e to the xy times the derivative of the first, 1. I'm xy, and I know it. All right. So anyway, so that's the outside derivative for x. Taking the derivative of x with respect to t, we get 2t plus the partial of z with respect to y. Now that's not too hard. That's just going to give us x e to the xy times x. And then we're going to multiply that by, well, this is t to the negative 1. So that becomes negative 1 over t squared, the derivative of t to the negative 1. And there's our derivative. Now, of course, we do want this with respect to t. So what you could do is you could replace now your x and y with the t component, with the t's. For example, x is t squared, y would be t to the negative 1, and you can replace that. Now, that's one way we could do the chain rule. Now, the other way we can do the chain rule, and this is what they're talking about, choose the appropriate chain rule, is just use what we learned last year. In calculus, I could replace it. Z would equal, if I replace the x, we would get t squared times e, and if I multiply those together, we get t. X times y, t squared times negative 1 would become t. Therefore, if I take the derivative, dz dt, we would use our product rule, the first times the derivative of the second, plus the second times the derivative of the first. And there's our derivative. And these are the same, and you can prove that by plugging in your t values and simplifying it. So, the one thing to kind of remember, like Bryce said, the one thing to remember is that when we're doing these, is it doesn't matter which one you choose to use, just whichever one's easier. Sometimes it's easier to do using our total derivative. Sometimes it's easier just to use our simplification from our derivative rules from last year. Now, I do want you to remember, these are in terms of only t. So, recall, these are traces. Because they're in terms of t, they're traces of a 3D function, of a 3D graph. So we're talking about how a 3D function is, how a 3D graph is changing along a trace. So kind of like imagine hitting a golf ball like that, right? The golf ball is hitting in the air. We're talking about the rate of change of that golf ball as it flies through the air. But remember, golf balls don't only travel just in the flat surface. Golf balls, if you look on one side, they kind of look like this, but if you look on one side, but if you look straight on, a golf ball could be hooking at the same time. And that's kind of what this can kind of help us solve here later on. So, like if a golf ball is traveling through the air, it can kind of go, it wiggles through the air sometimes. Or at least that's what mine always do. Mine never go in a straight line. So let's take a look at another one here. So, alright, so we have z equals x squared y cubed plus y cosine x. And they tell me x is natural log of t squared and y is equal to 4t. Alright, so I have a choice. I could use my total derivative, like we did up here, or we can replace. Now, in this case right here, I do think it's easier to replace and take the derivative. But this one, I'm replacing natural log of t squared, and then I'm going to what? Oh yeah, square that. That's a lot of nasty little chain rules right there. So for this one, I might choose to use my total derivative. Now, important to remember, t is our independent variable here. So this is a single variable, can't spell variable, there we go. So t is our independent variable. So this is only a single term right here. So if I want to find the derivative of z with respect to t, partials, I'm going to use my partials, not my derivative from last year, but use my partials here. And this is going to equal, well, I have to use the x's and then the x with respect to t. So the partial of x, the partial of z with respect to x times the partial of x with respect to t. And I do the same thing for the y's. The partial of z with respect to y times the partial of y with respect to t. And we can do this in our heads. If I look at the partial z only with respect to x, there they are. This is going to give me x squared 2x y cubed plus the derivative of y cosine of x. So that becomes a minus y sine of x. Now, I have to multiply that by the derivative of x with respect to t. So I took the derivative of x. Now I have to take care of its inside. Remember, I'm replacing this x with natural log of t squared. This is my inside function. So when I take the derivative, I have to take the derivative of the inside next. And that's easy. That's just 1 over t squared times 2t. Don't worry about simplifying. And then we do the same thing for the y's. Plus, take the derivative of z with respect to y. We would get 3x squared y squared plus, this just stays cosine of x. And then we take the derivative of sine of 4t, which becomes times 4 cosine 4t. Remember, the 4 comes from the chain rule itself. And there is our derivative. I don't simplify, I leave it alone. Alright, so anyways, to kind of give you an idea about what we're kind of doing here, let's take a look at this in another quick perspective here, right here, real fast, okay? So remember, what we're doing is we are substituting in this x for this x squared. So let's just only deal with that. This is really saying the natural log of t squared squared. If I only deal with the x squared part, I'm not dealing with the y's or the x over here. When I'm taking the derivative of the derivative z with respect to t, this is my chain rule. I take the derivative of the outside, which becomes this 2 times, there's my x, natural log of t squared to the first, times the derivative. Now remember, I'm not worried about all this other stuff. We're just dealing with the 2x. And now I have to take the derivative of the inside, which becomes my 1 over t squared times 2t. So that's really kind of what we are doing. It's just easier sometimes this way because I don't have to deal with all those. I mean, look at that. There'd be a chain rule, another chain rule within a chain rule, a chain rule within chain rules. It just becomes a nightmare. So sometimes our total derivative or a partial way is a little bit easier to do. All right, I hope you enjoyed this video. Go on to video number 2. We'll take a look at some more examples. Bye-bye.